Today we are going to learn about kernel tricks and support vector machines. In this session, we will explore how kernel functions transform data into higher dimensions to improve model accuracy for complex datasets. You'll gain insights into choosing and implementing the right kernel for various scenarios, enhancing your SVM performance.
Welcome to this session on kernel tricks and support vector machines. In this video, we'll explore the concept of kernel functions. Kernel functions are mathematical tools that transform input data into higher dimensions, enabling support vector machines, SVMs, to classify data that is not linearly separable in its original form. By mapping data to a higher dimensional space, kernel functions allow SVMs to find a hyperplane that can effectively separate different classes. This transformation is crucial for improving model performance, especially when dealing with complex datasets. Understanding kernel functions is foundational to mastering SVMs, as they play a pivotal role in enhancing the algorithm's ability to handle nonlinear data.
In this block, we'll delve into the differences between linear and nonlinear data classification. Linear data can be separated by a straight line, making it relatively easy for SVMs to classify. However, real-world data is often nonlinear, meaning it cannot be separated by a simple linear boundary. This is where kernel tricks come into play. By using kernel functions, SVMs can transform nonlinear data into a higher dimensional space where it becomes linearly separable. Visualizing the data in both its original and transformed states can help in understanding how kernels enable SVMs to handle complex classification tasks. Selecting the right approach, linear or non-linear, depends on the nature of your data, and kernel functions provide the flexibility needed to adapt to different scenarios. Next, we'll explore the common types of kernels used in SVMs and their applications. The linear kernel is the simplest type and is used for linearly separable data. The polynomial kernel, on the other hand, can handle more complex data by introducing polynomial degrees into the transformation. The radial basis function, RBF, kernel is perhaps the most popular for nonlinear data, as it can map data into an infinite dimensional space. The sigmoid kernel, which mimics neural network activation functions, is another option for certain types of data. Each kernel has its own strengths and is suited for different types of problems. Understanding when and how to use each kernel is crucial for optimizing SVM performance. Let's dive into the mathematical foundation of kernel tricks. At its core, the kernel trick is a method that allows SVMs to perform computations in a high-dimensional feature space without explicitly transforming the data into that space. This is achieved by using kernel functions to compute the inner product of two data points in the feature space. The beauty of this approach is that it simplifies the computational process, allowing SVMs to efficiently handle high-dimensional data. By leveraging kernel functions, SVMs can focus on the relationships between data points rather than their explicit transformations, significantly improving the algorithm's efficiency and effectiveness. Choosing the right kernel for your data is a critical step in optimizing SVM performance. Several factors should be considered, including the characteristics of your data, the degree of nonlinearity, and the computational resources available. Understanding the properties of your dataset can guide you in selecting a kernel that aligns with your classification goals. Sometimes, a trial and error approach is necessary, experimenting with different kernels to find the best fit. The choice of kernel has a direct impact on model performance, so it's important to follow guidelines and best practices to make informed decisions. By carefully selecting the right kernel, you can enhance the accuracy and efficiency of your SVM model.
In this block, we'll investigate the performance implications of different kernels. The choice of kernel affects not only the accuracy of your model but also its computational efficiency. Some kernels, like the RBF, can lead to longer computation times due to their complexity, while others, like the linear kernel, may offer faster results but at the cost of reduced accuracy in nonlinear scenarios. It's important to consider the available resources and scalability needs when selecting a kernel, as this will affect the overall performance of your SVM. Balancing the trade-offs between accuracy and efficiency is key to achieving optimal results, and understanding the performance implications of each kernel type can guide you in making the right choice. Now, let's look at how to implement kernels in Python. Python offers several libraries for SVM, with scikit-learn being one of the most popular options. Implementing kernels in Python is straightforward, thanks to the comprehensive tools and functions provided by these libraries. We'll walk through practical coding examples, demonstrating how to apply different kernels to your dataset using scikit-learn. By running these examples, you'll learn how to interpret the results and adjust your model parameters to improve classification performance. Understanding how to implement kernels in Python is an essential skill for data scientists, enabling you to leverage the power of SVMs for complex data analysis tasks. To wrap up our discussion, let's explore some real-world examples of kernel applications. In finance, kernels are used for fraud detection and risk assessment, where complex patterns in transaction data are analyzed. In healthcare, kernels help in diagnosing diseases through medical imaging and patient data analysis. Image recognition is another area where SVMs with appropriate kernels excel, providing high accuracy in identifying objects and patterns. Natural language processing also benefits from kernel applications, enabling more nuanced understanding of text data. By examining these real-world scenarios, we can appreciate the versatility and power of kernel tricks in SVMs, providing valuable insights into how these techniques can be applied across various industries. As we conclude our session on kernel tricks in support vector machines, let's recap the key takeaways. We've learned that kernel functions are essential for transforming data into higher dimensions, enabling SVMs to tackle nonlinear classification problems. The choice of kernel significantly impacts model performance, and understanding the characteristics of your data is crucial in making the right selection. We've also explored practical implementation techniques in Python, providing you with the skills needed to apply these concepts in real-world scenarios. Remember, mastering SVMs and kernel tricks requires continuous learning and exploration, as the field of machine learning is constantly evolving. We hope this video has equipped you with valuable insights and practical knowledge to enhance your data analysis capabilities.